Okay, so last class was our project check-in day. So thinking about the projects, let's just take a look and make sure we're all clear on when they are due. So the steel drum is due on the 27th. I guess that's this Friday. And then the pipeline project is due on a week from today, the coming Monday. Okay, so Friday and then Monday are when the two projects are due. What is due right now is quiz number 2, so throw it into the green folder in whatever form it is in. This is the only time that I will take that. There aren't lateness penalties associated with turning it in late, like it has to be in now. So put it in the folder even if it's not all the way done. And I'll get that back to you on Wednesday. Also, I talked on Friday about the quiz number 3, this derivative rules quiz. So it is officially assigned right now, and it is due at the start of Wednesday's class. And you have several copies of this quiz already. They're the first few pages of this packet, okay? So just read the directions carefully for that quiz. It's different from all the other quizzes that we take this semester, but the directions are laid out clearly for you. So that will be due Wednesday first thing. And today we're going to talk about derivatives of trig functions. Any questions on the calendar? Okay, then let's jump in here. I think we're on page 39. Today we discover formulas for the derivatives of trig functions and use them with other derivative rules to solve optimization problems. Number 1, below is a graph of y equals sine x. We don't yet have a way to differentiate this function, but let's try to sketch the graph of its derivative on the same axes right here. So when I'm sketching the graph of a derivative function, I like to start with my places where the original graph is flat. Do you see the two places where this graph is flat? Right there and right there, yes? And so what's the value of the tangent? What's the value of the derivative at those 2 points? 0. So I'm going to be plotting points in orange. The orange is going to be the derivative, so I'll just mark it up here. This is going to be y prime in orange. And so we're just copying the same x's as before, but making 0 for the y, 0 for the slope. Okay, and then how about we just draw 3 other tangent lines, maybe a little tangent line at the origin. So just ballpark tangent line at the origin, and then maybe another tangent line where it hits the x-axis, something like that. And then maybe one more tangent line where it hits the x-axis again. So just ballparking these things. And then the first tangent line, it actually does go through some of the background grid points. What does it look like the slope is? Sure looks like it's a 1, so let's go ahead and at that same x value put a y value of 1. And then if I believe that that first slope is a 1, what do you think about this like corresponding point? It's got to be a -1, right? Okay, so then right there, right below, it's not 3, it's a little bit bigger than 3, right? It's pi. So you go down to -1, and then finally the 2 pi point is the same as the 0 point. So if I called it 1 before, then I guess I got to call it 1 again. So I've got these 5 points, and then I'm going to connect the dots. Now there's lots of ways to connect the dots, but what I don't want you to do is this, right? I mean, like it's smoother than that. There isn't like some rough transition that happens right there at the bottom. So we connect the dots in what we feel like is kind of a smoothish way to hit these points, and we get something like that. And then we say, oh my goodness, that looks an awful lot like one of our other trig functions. What does it look like? Cosine. And it turns out it is cosine. So that is our answer here. The derivative of sine of x is cosine of x. I've been teaching this for a long time. This one still gives me goosebumps. The derivative of sine of x should not be as clean as cosine of x. It is crazy that it works out. Think about the unit circle. You got a point, you go up to some angle, right, on the unit circle, you pick your point, the cosine is the x value, right, the sine is the y value, and you graph and you get these really nice like curves from 108, the graph of the sine function, the graph of the cosine function. But somehow, if you look at the curve, the sine function, that's the original one that was graphed up there, that came from the y coordinate on the unit circle, and you find the tangent line for any old point, it turns out to just be the x coordinate on that same unit circle. It's the x coordinate of the same point, which is like, it's just silly, but it works. Okay, chain rule says then if we're doing sine of stuff and we want that derivative, then it becomes cosine of what? Stuff. right? And then times the derivative of the stuff. Okay. So I had planned on doing the same thing for the cosine graph. So there's cosine, and we were going to draw some tangent lines and estimate or draw the graph of the derivative. I'm not going to do the whole thing out, but just to save a little bit of time, let me make one observation here. At this spot right here, the slope of the tangent line is maybe -1. So that means at that spot right there, it's down there. The derivative would be down here. Is that going to be the sine function? Like some people think, oh, if sine becomes cosine, then cosine becomes sine. If I try to draw and connect, this is not the sine function. Turns out it's just the negative of the sine function. So let's fill in here. Derivative of cosine of x is negative sine of x. And therefore, derivative of cosine of stuff, negative sine of stuff, times the derivative of the stuff. Okay, so sine becomes cosine, cosine becomes negative sine. It turns out that all 6 trig functions have a derivative. Here are all 6 of them written out in one spot. We've seen the top row already. Sine becomes cosine, cosine becomes negative sine. 4 new ones. Tangent becomes secant squared. Derivative of tangent of x is secant squared of x. Derivative of cotangent is negative cosecant squared of x. And I just want to point out the similarities between these two. Tangent becomes cotangent, secant becomes cosecant. Squared is still squared. What's the only other change? Negative. Okay, and then down here, the last of the 3 main ones, derivative of secant x is secant x times tangent x. When I say that one, you're going to hear me say secant tangent, but it's multiplication that I'm talking about. And then take a look at the derivative of cosecant is negative cosecant times cotan, which is exactly the same pattern that we had one row above, right? Secant became cosecant, tangent became cotangent, positive, negative. And in fact, that same pattern held true kind of up here. Cosine became negative sine. All 3 on the right-hand side are negative. All 3 on the right-hand side start with the letter C. Derivatives of all of the co-functions, there's 3 of them, are all negative. The derivatives of the not co-functions are all positive. And like if you just memorize it in this table, makes it easier because there's all these patterns floating around. Okay, so your job is to memorize these formulas, just practice them a couple of nights in a row and you'll have them. I just want them to roll off the tongue in the same way that like you know the power rule now and you know the product rule and you know the quotient rule. 6 of these guys, just a little bit of practice. Okay, in the activities, you are going to prove that the derivative of tan is secant squared. And you are also going to prove that the derivative of sine is cosine. I know we looked at the graph, but the graph is not proof, right? The graph is evidence, but it doesn't mean for sure that it works out perfectly. So you're going to prove rigorously these 2 during the activities, but you're going to start in the activities by using them. So next page, and let's see if we can get through.